Greetings once again. My name is John Gabriel, and this is a new calculus channel. So, if you'll recall, in the previous video, I was discussing Professor Dave Explains, and he was talking a lot about double integrals and triple integrals and whatnot. And he had some answers in which he, for example, had I think a negative volume. Now, you cannot have a negative volume or a negative area. So, because Professor Dave is an idiot, just like all math professors, mainstream professors, they don't realize that if you have a function like this and you calculate areas like that, you have to split the areas uh, above the axis with below the axis. And the same thing happens with volumes. You can't. And why is that so? It's because the integral is, as I revealed to the world, a product of two arithmetic means. Okay, this is something I revealed, nobody else. Okay, I take all the credit for it. It requires genius, of course, to reveal this, but your professors are morons. So basically, to find area, it's a product of two arithmetic means, right? So if you have, and that's why it's called quadrature, because you have a height and a length. Okay. And so the height is the level magnitude, which is a better term than arithmetic mean because it has nothing to do with the middle of anything or relative position. And length is the level magnitude of all those lines. So as you can see here, there's nothing even about real number. I mean, the Britannica has an entry on the mean value theorem which talks about D properties of real number. That's absolute bullshit. And it's quite funny because just the other day I was explaining to, I think, a PhD or a master's student, uh, and I was explaining the concept of the level magnitude. So I explained first simply using uh, three piles of blocks, this one with 3, 2, 1, and he said, "Oh yeah, but you'd have to show in real analysis that." If they're not in terms of units, then it'll still work. So I said, well, of course. First of all, it's not real analysis, and you don't need real numbers because the mean value theorem is not about real numbers, but level magnitudes. I shall show you in a moment now what I mean by that. But coming back to this thing about positive and negative areas. So the baboons of mainstream academia will refer to all this as, I think, the net change, okay, which is a bullshit term because it makes no sense adding areas or volumes that are negative. And the reason that this area underneath here is negative is because, or is due to the fact that you're taking an arithmetic mean of the y values between the curve and the x-axis. That's why it's negative. And if it's bigger than these areas, you're going to have a negative value. Like I said earlier, you got negative 17 or something like that, or 18. I don't remember. It doesn't matter. It's entirely senseless. So you cannot have negative volume or negative area. It's got to be positive. Doesn't make sense if it's negative. Right. So that is why the mean value theorem is very important, and very important that you're able to prove it. So let's look quickly. So this was the example I showed you. By the way, in this particular step here, this partial derivative of f is really also just equal to the total derivative, because you're only at this step here, you're only differentiating with respect to x and not keeping anything else constant. Now, if you recall, initially, let's just clear the canvas here. Initially, we had something which was like y plus 3x or something like that. I don't remember. And then we integrated this. By the way, this has to be a smooth function. And you say, well, how can it be a smooth function? Very easy. One of these is a constant. Okay. So the mean value theorem must apply to whatever this expression here is in a single variable. And of course, it doesn't matter how many integrals you have. The mean value theorem always applies, and this always has to be smooth, not only continuous, as the baboons of Wikipedia tell you, okay, in the fundamental theorem of calculus. It has to be smooth. So what that means is that if you have a curve like that, then in any given interval, say this interval, it must only be possible to produce one tangent line at any point in this interval. If except for inflection points, they don't count. And if that's the case, then we say that if this is f, it's smooth over this interval. Okay? Very important. And you'll see now why it's very important. So let's go to a look at the proof. So the mean value theorem, which is the fundamental theorem of calculus and the most important theorem in calculus, and I just need to clean my glasses here for a second, tells us that if you have a smooth function which represents the slope of a primitive function, then there is a level magnitude of all those slopes. Okay, so in my free ebook, I do it 3 times, and in this first case here, I do it using the bullshit machinery of mainstream calculus. In order to do that, we start off with thinking of the x coordinates as magnitudes. So we think of them as x plus k w over n, where w is the interval width. And we form the definition of the derivative as follows, okay? And we take omega as the interval width between x and x plus w. And of course, w over n, the equal width of each partition in x and x plus w. This isn't much different from the mainstream definition, which is really just obtained by inverting the sense of uh, this equation here, which equates h with omega over n, and then replacing h to get this form here, nd, okay? So using the new definition nd, we can define any of the positional derivatives. So we call, now positional derivative is just what I showed you in here. Sorry, it's what I showed you in here. Let's just draw this again. So if you have a curve like that, it's just the slope at this point, slope at this point, slope at every point. Now you'll see that it doesn't matter that we have the slope at every point, because if you think of it in mainstream terms, there are infinitely many of those, but it doesn't matter. Why? Because the smoothness of a curve means that all the slopes in the middle will cancel out in a telescoping sum, leaving only a difference of the primitive function. And this is a proof of it. So I define a partial, not a partial derivative, a positional derivative like this. So x plus kw over n means just one position inside this interval. It doesn't have to be a real number or anything. It's just a magnitude or a distance along, an equal distance along this interval, okay? And so we can think of the arithmetic mean, or rather the level magnitude, as the sum of all those positional derivatives divided by n. It's an arithmetic mean, isn't it? That's how you've been taught arithmetic mean in mainstream, isn't it? So you've always understood it as being the sum divided by the total, but you haven't really understood that it makes no sense if one can't redistribute the values. But that's very easy to do in calculus, because all we do is we just push all these down so we get a nice rectangle, okay? All the extra level magnitudes, these bits, we redistribute them. So here we've got them like this. Let's say we've got this. So we redistribute that bit so we can have them all flat and equal. And that will be the area. And I'll show you how that works in the proof. So we say let that equal to that, and then we replace each of these slopes with the positional derivatives, as you see over here, okay? So you replace each of the slopes with f prime of x, x plus w, omega over n, 2 omega over n, etc. And then if you expand each of these derivatives, this is how they look. This is the first expansion, and then the second one, and so on right till the end. And you'll see that all of them cancel out except the first and the last, okay? So ultimately you end up with n over omega times this, okay? And of course, there's no longer n in here, so the limit falls away and you land up with the ubiquitous statement, the identity of the mean value theorem. So it's pretty complicated in the mainstream calculus because you don't have well-formed concepts, but you can replace x by a, and letting omega equal to b minus a, you have the trivial or the ubiquitous form, which is how you see it in most textbooks. Okay, and then of course the fundamental theorem is derived in one step from this by multiplying both sides by the interval. Okay, so if we multiply both sides by the interval f prime of c, which is the level magnitude or arithmetic mean, as your moronic professors call it, then we'll have the integral, the product of two level magnitudes. These are the level magnitudes. Okay, good. So that's you can find all this in my free ebook. I'll place a link to it. Then also I've given you inside here a proof using the historic geometric theorem, and that's in the next chapter. I'll also show you how you can do fancy things with this positional derivative concept. It's still mainstream garbage, so I wouldn't recommend that you take any of the stuff too seriously. It's flawed concepts, ill-formed concepts. But anyway, then the historic geometric theorem. This is a new calculus, so and the historic geometric theorem is also in this file, in this ebook. Don't remember where it is now. Was it page 92 or something like that? Where is it? Oh yeah, here. Okay, so that starts historic geometric theorem. Similar thing happens. You get a telescoping sum after you take. So you start here again with the same interval, and you used the identity, the historic geometric identity. Okay, which is the expression. Let me just write it out. The historic geometric identity says f of x plus h minus f of x over h is equal to the derivative at x plus the difference in slopes. Okay. So this proof here is based on that. Okay, so it shows you how the q terms add up and how you get to the fundamental form, which is either this PC or MC. Okay, it doesn't matter which one, they're the same. And there's a reason that you have to subtract this. And you can read the reason here in the book, why you have to do that and why it's left over. That doesn't happen in the new calculus, because in the new calculus, you write f of x, from which I realized the historic geometric theorem, by the way. You write f of x minus like that over m plus n, and that's equal to f of x. And you can either leave it like this, or you can write plus q x comma m n. And the reason you can write this is due to the fact that the slope difference between the tangent line, that's supposed to be a tangent line and a parallel secant, is always zero, okay? It's always zero. So it doesn't matter which way you write it. This happens to be an auxiliary equation. Of course, you don't have the same feature in your bullshit calculus. If you do this, it's never true unless f is a linear function. And even then, it doesn't mean much and doesn't lead to brilliant new results like you find in the new calculus. So, and then of course, much later on, I give you a proof during the rigorous new calculus, which is down here, right at the end. Okay. So I first of all explain to you what the M and N's mean, and then I'll show you how you can do the same thing. I think I've done it already. And I give you some examples. Okay, I've probably done it a little bit earlier or later. Let me see. No, later. Okay, so here's the new calculus version. Again, the same story. You're summing up the ordinates. This doesn't mean the same thing as your mainstream calculus. Newton wasn't aware of this particular concept. He was getting to it in his last chapter of De Analysi, but he didn't know about it. Otherwise, he probably would have discovered this before me. And this is a new calculus proof. Again, you'll notice the beautiful telescoping sum. You end up with the new calculus definition. Okay? And of course, again, the integral is a product of two level magnitudes. And of course, that's demonstrated beautifully here, where we can show that, okay, we have an auxiliary equation. This is a very advanced feature. Remember I told you Q of x m n equals to 0, and you can use it for a lot of things, but I'm not going to go into that now. And the proof here is that you can vary k to any value you like, right? To 2 or 3 or 4. And the result, 12.6, will always be the same, okay? You see that? So this is the level magnitude, okay? This 12.6 here. And if you change them, let's say like that, it becomes 15.8. So again, always 15.8, okay? It's a beautiful little proof of the mean value theorem using the new calculus definition. So once again, if you're not already a subscriber on my channel, become a subscriber. Tell your friends about it. Follow me on academia. You'll see many interesting articles on academia. Okay. This is me, and you can just go to my profile. I'll put a link to it in the details section. And you'll find many, many, many articles and some videos. I think over 210 articles already and 3 books. So the books that are featuring are the non-fictional origins and history of calculus, and also the ultimate book of numbers. And they're written in a format that even if you haven't had any background training in mathematics, you will enjoy reading the book and understand more than you've ever understood in your entire school or university history or experience. So this is a new calculus channel. I'm John Gabriel. Till next time, goodbye.